Hello everyone. Today I'll talk about our work on how limit cycles within the Lorenz chaotic system can help us rationalize some counterintuitive transport behaviors for an active particle. Alright, so let's start with high school physics, so Newton's second law. So I'm sure you all must have come across this textbook problem. So if you have a block sitting on a flat surface, then the net force acting on the block is zero, and hence there is no motion. Now, if you tilt the surface a little bit, then intuitively you expect that the block will slide down in the direction of gravity, right? Now, this is what happens to any system at equilibrium, that if you have a system at equilibrium and you apply a small bias force in some direction, then the system will respond with motion in the direction of the applied bias, right? So another example would be that if you apply a small voltage difference across a wire, then you will get a current flowing in the direction of the applied voltage difference. Yet another example could be if you have a Brownian particle, right? So a particle that is undergoing random motion, and if you apply again a small bias force, then linear response theory tells us that you will get a drift of the Brownian particle in the direction of the applied bias. Now, this works for system at equilibrium. Now, what happens if the system is out of equilibrium, right? So if you have a system which is out of equilibrium and you apply a small bias, then what happens? It turns out that if you apply a small bias for a system out of equilibrium, then you can get counterintuitive phenomena in such systems. And one such behavior is known as absolute negative mobility, right? So let me illustrate this through a cartoon. So in a regular equilibrium system, what you are seeing here is that on the x-axis is the applied bias force, and the y-axis is the response of the system, right? So as we saw in those examples, if you have some applied force, then you will have a response of the system in the direction of the applied force, and you will get a positive slope on the curve when you plot the response against the applied force. Now, when you have absolute negative mobility, you have something that schematically looks like this. So for small value of the applied bias, you get a negative slope. So what this means is that as you increase the applied bias, you have a response that is against the applied bias, right? So that's absolute negative mobility. So this behavior, it has been observed in many systems, both classical and quantum. In particular, it has been extensively studied in minimal models of inertial Brownian particles. So when you have these Brownian particles and you make them out of equilibrium by applying external periodic forces with some bias, then you get these absolute negative mobility behaviors. Now, what I'll be talking about today is these anomalous behaviors in an active system, right? So for an active particle. Okay, so let me start by telling you what I mean by an active particle, right? So the working definition of an active particle that is used by researchers in this community is that an active particle is an entity that consumes energy and converts it into some sort of persistent motion, right? So the particle takes up energy and uses it to do work, mainly move around, and dissipate some energy in this process as well, right? So due to this active particle is out of thermodynamic equilibrium, right? So active particles come in all shapes and sizes, and they range from nanometer scale all the way to scales of tens and hundreds of meters. So right at the nanoscale, you have processes going on within the biological cell, such as molecular motors. You can model the cell itself as an active particle. So for example, here you are seeing a type of white blood cell chasing a bacteria. So the white blood cell consumes energy by taking up nutrients, and it's converting it into this crawling motion. Another example is an E. coli bacteria, which you see here. So again, the bacteria eats some food, and then here you can see it's converting it into this persistent run and tumble motion. There are not only living systems that are active, you can also have synthetic active particles. And an example is a mobile robot. So as you see in here, the robot is persistently moving and then changing directions. So it is an example of a synthetic active particle. Yet another example of a synthetic system, which we will focus on today, is this system of walking droplets. So you have droplets bouncing and walking on liquid surface of the same liquid as the droplet, right? So we'll explore the active system of the walking droplet. Okay, so this system is, if you take a container filled with silicon oil and you vibrate it vertically, then you can get a droplet of the same oil bouncing and walking on the liquid surface, as you see in the top videos. So as you see there, each time the droplet bounces, it creates a little wave around itself. The droplet then interacts with these waves on subsequent bounces to propel itself horizontally. Now, three key features to note about this system. First, the droplet and its underlying wave, they coexist as a wave particle entity. So if I were to poke the droplet and make the droplet disappear, the underlying waves would decay and the surface would become completely flat. Now, the second is that there is memory in the system. So the waves that are generated by the droplet, they decay very slowly in time. So the droplet is not only influenced by its most recent wave, but also by the waves it generated many bounces before, right? So there is memory in the system. And lastly, the system is active, right? So even though the whole container is vibrated up and down, the droplet locally takes up that energy through creation of these waves, and it converts it into this persistent motion. Right, so therefore I like to think of these droplets as active wave particle entities, right? And you can see on the video on the right that you can have this very interesting interactions between them, and it's not very difficult to build this setup, and you can make a DIY setup yourself. If you have a look at that link, it has some instructions. Okay, so what we are now going to consider is we are going to consider a simple model of this system. So we are going to look at what's known as the stroboscopic model that is widely used to model these walking droplets. So the video you are seeing there on the top left, it's the same video from experiments as in the previous slide. The only difference is that the video is strobed at the bouncing frequency. So there is only one image of the droplet per bounce, and hence you don't see the bouncing motion and you only see the horizontal walking motion. So the model does exactly that. So in the model, you average over the periodic fast vertical bouncing and write down an equation of motion only for the horizontal dynamics. And we are going to simplify this further by restricting the droplet to only move in one dimension, right? Either left or right. So when you write down an equation of motion and non-dimensionalize it, you get an equation that looks what you have on there at the bottom. So the equation is essentially F equals ma, Newton's second law, for the particle, the droplet. So the first term there is mass times acceleration, an inertial term, and you can think of kappa there as a dimensionless mass. The second term models the effects of dissipation in the system. So there is a dissipative force due to aerodynamic drag and also momentum loss during impact. And this is modeled proportional to velocity. The term on the right hand side, the horrible looking integral term on the right hand side, that's the force that the droplet experiences from the wave that it generates, right? So let's try to understand what that term is step by step. So here we are saying that at each instant, the particle generates a wave of shape a of x, and that gradient of those waves is what propels the droplet. Now, you also have to integrate over all the waves generated in the entire history of the droplet, right? So The reason you have an integral from negative infinity to t is we are integrating over all the history of the droplet, and the function f there is the gradient of the wave, which is a, right? And the exponential with a decaying time there is there because the waves generated by the droplet, each of them decay exponentially in time, right? So the term on the right hand side is an overall wave field that is obtained by integrating over all the waves through the entire history of the droplet, and you take the gradient of that to get the force on the droplet. And the parameter beta there is again a dimensionless wave force coefficient, right? So we have a complicated integral differential equation which you see there that describes the motion of the droplet. Now, in the experiments, you see that the shape of the wave that the droplet generates has both oscillations and it decays spatially away from the droplet. Now, we are going to make a simplification and only take into account the oscillatory nature of the shape of the wave and ignore the decay, right? So we are assuming that the shape of the droplet generated wave is a cosine function, so therefore its gradient would be a sine function, and that's why we have a sine in the equation here, right? Now this simplification still captures the key working dynamics of the droplet, but what it does is it allows us to simplify the equations, right? So this particular equation now, we can show that it maps onto a set of ordinary differential equations. So we have gone from an infinite dimensional integral differential equation to a set of three nonlinear coupled ordinary differential equations. And these equations are the classic Lorenz equations where chaos was first reported, right? And the connection here, or the mapping between the two equations, is as follows. So the capital X variable in the Lorenz equation maps to the velocity of the droplet or the particle. The capital Y variable in the Lorenz system is this wave memory force on the right hand side of the droplet's equation, and the capital Z variable is related to the height of the waves at the location of droplet. And the parameters sigma, r, and b in the Lorenz equations map in a one-to-one manner onto the kappa and beta of the droplet's equation, right? So we get this one-to-one mapping, and we can go from an integral differential equation to the Lorenz system to understand the dynamics of the droplet. Now, for the droplet system, it turns out that you can get more physically relevant dimensionless parameters if you rescale the system, right? So we are going to go from this kappa and beta parameters that we have here to this r and tau parameters by just rescaling the variables, right? So we still have the Lorenz system, but we have just rescaled it. So we now have the parameters r and tau, and then r can be thought of as a dimensionless wave amplitude, right? So the dimensionless amplitude of the waves generated by the droplet, and tau can be thought of as the rate at which those waves decay, right? So that is the memory of the system. All right, so what we are going to do now is we are going to fix R, and we are going to increase the memory and see what the Lorenz system exhibits and try to relate that to the motion of the droplet. So at very small values of tau, in the Lorenz system, there is a single stable fixed point at capital X equals 0, right? So now, if you remember, capital X is the velocity of the particle. So capital X equals 0 means I have a stationary particle, and you can see that on the position versus time plot on the right, right? So you have these two curves, blue and red, which correspond to two different initial conditions, and you can see that they become flat, so there is no motion of the particle. And this is something that is observed in experiments at small memory. Now, as you keep on increasing the memory, you get a pitchfork bifurcation in the Lorenz system, and the stationary state becomes unstable, and you get two new stable points. So one with a positive x and one with a negative x. And if we plot the corresponding trajectory for the particle, this shows something that you see on the right. So you have a position versus time at a constant slope, which means we have a constant velocity of the particle either moving to the right or moving to the left. And again, this is something that is observed in experiments, right? So you have these steady walking states. Now we can keep on increasing memory in the Lorenz system, and you get a complex set of homoclinic and heteroclinic bifurcations in the Lorenz system as you keep increasing the memory. But eventually, at sufficiently large memory, you get chaos in the Lorenz system, right? So in the Lorenz system phase space, you have a chaotic attractor. And what this corresponds to for the droplet, as you see there in that video, is that when you go from one wing of the chaotic attractor to the other wing, my particle moves from left to right, and it does this in a chaotic fashion. So I have a particle doing a random walk from left, jumping between left and right. Now, one thing to note is that even though the particle is moving randomly between left and right, there is a symmetry. So if I were to look at what is the net drift velocity of the particle, the average velocity over time, it would be 0, right? Because it on average, it goes equally to the right and the left. Okay, so now what we are going to do is we are going to add a small bias force to our equation of motion, right? So this bias force F, and if we add this to the equation of motion for the particle, and we again transform it into this Lorenz-like system, then this results in an extra term F being added to the x dot equation. Right, so we have a Lorenz equation now, but with an additional constant, which is F. Right, so now let's have a look at what happens to the average velocity of the droplet as a function of this bias force. So if we plot the average velocity of the droplet as a function of this bias force, you get something like this. So the two curves you see there are for different values of r and tau. So r is fixed to be the same value, and you have two different values of memory. And the results you're seeing there are averaged over time and also over different initial conditions, right? So if I had a Brownian particle, which is driven by thermal noise, then when you add a bias force, then you would expect the particle to just drift in the direction of the applied bias. Now, what we are seeing here is that as you increase the bias force, so first of all, when bias force F is 0, my average velocity is 0, right? Because as we saw before, when it's doing chaotic motion, there is no net drift. Now, as I add bias force, you get a proportional increase in the drift velocity on this blue curve, right? But then suddenly you get these weird states where you have a sudden jump in the velocity in the blue curve and a sudden decline in the average velocity on the red curve, right? So you have a negative mobility region. So even though my bias force is positive, my average drift is negative. And you also have a very giant positive mobility region where you suddenly have a jump to very large drift. So let us try to investigate what's going on here by plotting the trajectories. So if we plot the trajectory of the particle, it turns out what's going on when you have these big jumps, either positive or negative, is that those states correspond to periodic motion of the system. So within the chaos in the Lorenz system, there exist periodic orbits. Now, if those periodic orbits are asymmetrical about the capital X, then this means that there will be, on average, a net drift of the particle, right? So the two limit cycles, periodic orbits, which are asymmetric here, they occur in pairs because they still have to satisfy the symmetry of the Lorenz system. And one of them corresponds to a net drift in the positive direction, and the other one corresponds to a net drift in the negative direction. So if we try to summarize all the different type of trajectories in the parameter space, when there is no bias force, then it looks like this. So on the left parameter space, the color represents the average velocity of the particle, right? And the numbers 1, 2, 3, and 4 represent the 4 different types of trajectories that we get, right? So type 1 is a stationary state, which is not moving, so there is no average velocity, it's 0. The second one is a steady walking state that we saw, so there is a constant average velocity, and in this case it's positive because the initial condition has been chosen to give you a positive steady motion. In region 3, this is where chaos happens, and you can see that on average it's white region, so there is no net drift of the particle when there is no bias force. Now you get these bands these bands in the parameter space where you can see that there is very high positive and negative drift, and these correspond to the states we saw, right? These are the asymmetric limit cycles that give positive and negative drift. But note that they are highly mixed along this band, right? So even though you have these states, depending on the initial conditions, it's very sensitive whether you would get a positive state or a negative state. All right, so now let us try to see how this parameter space changes when we add the bias force and progressively increase this. So as you see there, as the bias force increases, the band of periodic orbits, they split and separate in the parameter space, right? Right, so without the bias force, we have a single band on which both of these positive and negative asymmetric limit cycles that gives net drift exist. And then in addition, when you add the bias force, this band splits into two. The positive drift states separate from the negative drift state, and then they migrate in the parameter space. So what this means is that if our parameters happen to be in the chaotic regime, which was just below the band, then as you increase the bias force, you would be swept by this red band, and this would be perceived as negative mobility for the particle. Whereas if you were above this band in the chaotic state, when there was no bias force, and then you introduce a bias force, then you would be swept by the blue band, which is the positive mobility band, and you would have a sudden jump in the average drift in the positive direction, right? So what we have found is that in this system, we have a nice mechanism for understanding the origin of these anomalous transport behaviors, right? So this giant negative mobility and also the giant positive mobility. And here we can attribute these to the periodic orbits that exist within the chaos of the Lorenz system, right? So even though we have explored this specific system, the mechanism that we find here might be more general to other non-equilibrium systems as well, right? So if you have a non-equilibrium systems that can be described by low-dimensional chaos, such as the Lorenz system, then there would be periodic orbits within the chaos. And then if a bias force is applied to such systems, then these periodic orbits may split and can give rise to these anomalous transport behaviors. Okay, so in conclusion, we saw that a simple model of this hydrodynamic active system of a walking droplet can be mapped onto the classic Lorenz chaotic system. And then by adding a bias force to this system, we found that we get anomalous transport behaviors of the droplet, where the average velocity can be giant and negative to the applied bias force, and also giant and positive to the applied bias force. And the neat thing is that in this system, we can track down the dynamical mechanism that gives rise to these anomalous transport behaviors. And in this case, we found that the asymmetric limit cycles that corresponds to a net drift of the particle, these limit cycles existing within the chaotic sea, are responsible for these anomalous transport behaviors for the particle. Thank you for listening, and here are the two relevant papers for this talk, and you can scan the QR code on the left for the paper and the QR code on the right if you would like to see some videos of these droplets. Thank you.